In this episode, we focus on a design decision that sounds small until you realize it quietly determines what happens at the worst possible moment. When the system is stressed, something is broken, and people are counting on it to behave predictably. Fail open, fail secure, and fail closed are phrases used to describe how a system behaves when it cannot perform a normal function, such as verifying identity, checking authorization, contacting a dependency, or reading a configuration. Beginners often assume that the safest choice is always to deny access and stop everything. But that can create mission harm that is unacceptable, especially in systems that support critical services. At the same time, allowing operations to continue when security checks are broken can create confidentiality and integrity harm that may be even worse than an outage. The right answer depends on mission logic, which means you choose failure behavior based on what the system is for, what harms are unacceptable, what degraded modes are safe, and what evidence and accountability exist when exceptions occur. This is not a purely technical choice. It is a risk governance choice expressed through system behavior. When you learn to select fail behavior deliberately, you build systems that respond to failure with controlled, defendable outcomes rather than chaotic improvisation. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To make these ideas clear, begin by anchoring them in plain language. Fail open generally means that when a control fails, the system defaults to allowing an action to continue, often prioritizing availability and continuity over strict enforcement. Fail closed generally means that when a control fails, the system defaults to denying the action, prioritizing confidentiality and integrity boundaries over continued operation. Fail secure is closely related to fail closed, but it emphasizes that the failure mode itself preserves security properties, such as preventing unauthorized access and preventing unsafe changes, even if the service becomes less available. In everyday terms, fail open is like a door that unlocks when power is lost, while fail secure is like a safe that remains locked when power is lost. The challenge is that both behaviors can be correct, depending on what is being protected and what consequences follow. Beginners often hear these terms as if one is good and one is bad, but in engineering, they are choices that must be justified. Mission logic is what provides that justification, because mission logic tells you which outcomes matter most under specific failure conditions. Mission logic starts with understanding the system's purpose and the kinds of harm that matter most in its operational context. If the system supports a mission where delayed access could cause immediate harm, such as critical services delivery, then availability may be the top priority in some scenarios. If the system protects highly sensitive data or controls high-impact actions, then confidentiality and integrity may be the top priorities, even if availability suffers temporarily. The point is not to pick one property forever. It is to identify which property is dominant for specific functions and failure situations. Many systems contain a mix of functions, some of which are safety critical, some of which are data sensitive, and some of which are convenience features. A mature approach chooses fail behavior per function and per control boundary, rather than applying a single global rule. Beginners should learn that the system's behavior and failure should align with the risk context and decision criteria you established earlier, because those criteria are how the organization defines acceptable trade-offs. When failure behavior matches mission logic, it becomes easier to defend decisions after incidents. Fail open can be appropriate when the cost of denial is higher than the cost of controlled exposure, but controlled exposure is the key phrase. If you choose fail open, you should be deliberate about what is allowed and for how long, and you should ensure that the system produces evidence and constraints that limit damage. For example, a system might allow limited read-only access during a dependency outage so critical workflows can continue, while preventing high-impact write operations that could alter data integrity. A system might allow a small subset of essential functions while disabling administrative actions and sensitive exports. The goal is to preserve mission continuity without granting broad, unbounded trust in a moment when normal verification is unavailable. Beginners often imagine fail open as full access for everyone, which is rarely defensible because it creates a wide attack surface during a period of reduced control. A more defensible approach is a constrained fail open mode that preserves core mission function while limiting privilege and minimizing exposure. This is where mission logic guides you to choose what can safely continue and what must stop. Fail closed is appropriate when the harm of unauthorized access or unsafe action is greater than the harm of temporary denial, which is often true for privileged actions and sensitive data. For example, if identity verification fails, granting administrative access would be a severe integrity and confidentiality risk because it could allow unauthorized changes that are hard to detect and reverse. If authorization checks fail, allowing a high-impact transaction to proceed could corrupt records or create irreversible consequences. Fail-close behavior preserves the safety boundary by making the system refuse action when it cannot confirm policy, and this can be the right choice even when it causes an outage for certain functions. Beginners sometimes worry that fail-closed is too harsh, but for many control points, harsh is exactly what prevents catastrophic harm. The key is to ensure that fail-closed does not create uncontrolled chaos, such as repeated retries that overload the system or unclear error states that confuse users and operators. Fail-closed must be paired with clear signals and a recovery path, so people know what is happening and how to restore normal function. When the system fails closed predictably, it can be safer and easier to manage than a system that fails open unpredictably. Fail secure, as a mindset, pushes you to design failure behavior that preserves security properties while still supporting recoverability and operational clarity. A fail-secure design might deny unauthorized actions, prevent unsafe state changes, and preserve audit evidence, while allowing the system to degrade gracefully for non-critical functions. It also means the system should not silently lower its security posture when something breaks, because silent posture collapse is one of the most dangerous failure patterns. For example, if logging fails, a fail-secure approach might limit certain high-risk actions until logging is restored, because operating without visibility increases impact if something goes wrong. If a key validation component fails, a fail-secure approach might prevent data writes to protect integrity, while still allowing reads for continuity if reads are safe. The emphasis is that security should not depend on components that can fail without consequence. Instead, security should be preserved as a priority during failures. Beginners should learn that fail secure is not the same as making the system unusable. It is making the system predictable and safe under failure conditions. Predictable safety is what allows mission leaders to decide whether to continue operations in a degraded mode or to pause until recovery. A crucial part of choosing fail behavior is identifying what is actually failing, because different failures warrant different responses. A dependency outage that prevents a non-critical lookup is different from a failure that prevents authentication, and a failure that prevents authorization is different from a failure that prevents audit logging. If the system cannot verify identity, the risk of impersonation rises, so access should become more restrictive. If the system cannot check authorization, the risk of overprivilege rises, so high-impact actions should be blocked. If the system cannot validate data inputs, the risk of integrity corruption rises, so write operations might need to pause. If the system cannot log, the risk of undetected harm rises, so the system might need to restrict actions that would be difficult to investigate later. Beginners often lump all failures into the same category and then argue about a single policy, but mission logic requires you to map failure types to the security properties they threaten. That mapping allows nuanced, defensible behavior rather than a one-size rule that is either too permissive or too disruptive. This is also where operational risk context matters because it tells you how much disruption is tolerable and what recovery expectations exist. Choosing fail behavior also involves thinking about attacker behavior during failures, because attackers often exploit degraded states. A system that fails open broadly during identity outages can become a perfect opportunity for unauthorized access if attackers can trigger or coincide with the outage. A system that fails closed but provides confusing error paths can create opportunities for denial of service or for users to circumvent controls through manual workarounds. A system that fails secure but lacks clear communication can lead to rushed emergency exceptions that expand risk more than necessary. Mission logic, therefore, should include the recognition that failure conditions are high-risk periods, not neutral periods, and your design should assume that both accidents and adversaries can take advantage of instability. This does not mean you design for paranoia. It means you design for predictable containment and clear boundaries under stress. Beginners should understand that resilience and security are connected here, because a resilient system that fails gracefully reduces the chance that people will improvise unsafe behavior. When you anticipate adversarial timing and human stress, your fail behavior choices become more robust. Another essential element is the role of human procedures and governance in supporting fail open or fail closed decisions. If you choose a constrained fail open mode, you need strong accountability and monitoring so that expanded access is visible, time-bounded, and reviewed afterward. If you choose fail closed for critical functions, you need clear escalation and recovery procedures so mission leaders can authorize emergency actions in a controlled way if mission harm becomes unacceptable. This is where roles, responsibilities, assumptions, and validation plans connect directly to fail behavior, because fail behavior is not only a software property, it is part of the system's operating model. For beginners, it is important to see that a design choice must be supported by operational capability, such as the ability to respond quickly to restore a dependency or to validate identity through alternate means. Without that operational capability, fail closed may cause prolonged mission harm, and fail open may persist longer than intended, increasing exposure. A defensible design considers both the automated behavior and the human decision process around exceptions and restoration. Validation is especially important for fail behavior, because failure modes are exactly where assumptions tend to break. A system might be designed to fail closed, but under load it might behave unpredictably, or a failover component might have different rules, accidentally failing open in certain conditions. A constrained fail open design might accidentally allow more privileges than intended if role mappings drift or if authorization rules are inconsistent across components. Fail-secure behavior might fail to preserve logs or might not clearly signal degraded state, undermining the very safety it was supposed to protect. This is why failure behavior must be tested and validated as part of the system's lifecycle, not assumed based on design intent. Beginners should understand that a failure mode that is untested is a risk, because the first time you learn how the system fails might be during an incident. Validation also includes confirming that monitoring detects the transition into degraded state and that recovery returns the system to normal without leaving residual unsafe settings. When failure behavior is validated, mission leaders can trust that the system will behave as expected under stress. A practical way to think about mission logic is to consider which losses are reversible and which are not, because reversibility heavily influences whether fail open or fail closed is defensible. Many availability losses are reversible, meaning service can be restored and backlogs can be processed, even if disruption is painful. Many confidentiality losses are not reversible, because once data is exposed, you cannot make the exposure unhappen, and the trust and legal consequences can persist. Many integrity losses are difficult to reverse, because corrupted data can propagate to other systems and decisions, and proving what was correct later can be hard. This does not mean you always choose fail closed, but it does mean you weigh irreversibility carefully. A mission might accept temporary downtime to prevent irreversible data exposure, or it might accept limited read-only access to prevent irreversible integrity corruption. Beginners should learn that mission logic is about balancing harms across time, not only about avoiding immediate inconvenience. When you think about reversibility, your choices become more defensible because they reflect long-term consequences, not only short-term pressure. The central lesson is that fail open, fail closed, and fail secure are not labels you pick once. They are behaviors you design intentionally for specific control points, guided by mission outcomes, risk appetite, and the nature of possible harm. You choose fail open only when it can be constrained, monitored, and justified by mission necessity, and you ensure it does not silently become broad trust during periods of reduced control. You choose fail closed and fail secure for actions where unauthorized access or unsafe changes would create unacceptable or irreversible harm, and you ensure the system communicates clearly and can recover promptly. You map failure types to the security properties they threaten, and you support the design with operational procedures, clear ownership, and validation so behavior under stress is predictable. When you do this, failure becomes a controlled condition rather than a chaotic surprise, and the system continues to serve the mission without quietly sacrificing the security boundaries that make the mission trustworthy. That is what it means to choose fail behavior using mission logic. And it is the kind of disciplined reasoning that turns security design from slogans into reliable system behavior.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.